Namaskar. Myself Professor Jaimala, presenting this lecture series on mechanics. Today in this lecture series I'll discuss about the canonical transformation. It is a transformation which is defined in phase space. So in this lecture I'll explain that what is the need of canonical transformation and when a transformation is called canonical. As I told you earlier that this is a transformation which is defined in phase space. And if we are talking about the phase space, we are talking about the Hamiltonian mechanics. So first of all, let us consider a system of n particles or a system which is described by n degree of freedom. So you are having a system of n particles, with n degree of freedom, right? And suppose your system, you are working in Hamiltonian mechanics. Then if Qi are generalized coordinates and Pi are corresponding momenta, then Hamiltonian H is defined as a function of Qi, Pi and time, right? And what are Hamilton's equations of motion? Hamilton's equations of motion are this is Qi dot is delta H delta Pi and Pi dot delta H delta Qi, right? Now imagine a situation. Your system is described in such a way that all the coordinates are cyclic, right? So suppose all Qi are cyclic, then it simply means that H will not have these coordinates. When you describe your H, it will not contain these coordinates. So what will be the partial derivative of H with respect to Qi? This is 0, right? And if this is 0, then equation 2, I'll write it in other type of numerals, it is 2. Then 2 implies that Pi dot 0 for all I. That means all the momenta are constants. Let these be L phi. Okay, so all momenta are constant, and when your momenta are constant, then H converts to your H is a function of P1 because coordinates are cyclic, Pn and probably of T, and this is equivalent to alpha 1, alpha 2, alpha n in time, right? So if I consider equation 1, then what 1 implies? Qi dot is delta H delta Pi or delta H delta alpha I, and from this expression you can find that if you differentiate H with respect to alpha i's, you will get an expression which is constant or probably a function of time. So I am writing it as, suppose it is Bi, it is a constant. Then you get Qi is Bit integrating plus some another constant of integration, and let it be gamma I. Okay. Now from this expression you see that you are in the position to get an expression which is in terms of Q's, that means generalized coordinates, and time. So your system has been described because these constants can be calculated with the help of initial conditions. So this is very easy. Suppose you are having a system, and in that system suppose all the coordinates are cyclic, then it is very easy to solve the dynamical system as you have seen here. I'll explain it with the help of an example. Suppose you are working in a field governed by the central potential, then H, I am talking about a dynamical system in two-dimensional plane, x and y plane. Then our H will be a function of x, y, momentum with respect to x, and momentum with respect to y, and probably of t. It may or may not be the function of time. Then we know that for the central potential system, H is described as px square upon 2m plus py square upon 2m plus potential function depending upon x square plus y square, right? So here x and y both are appearing in this expression. X, y both are present. Now suppose I convert it into, I am considering a transformation and I am converting into polar coordinates. So I am considering this transformation. Then H in terms of r, theta, it will be pr, it will be p theta, and naturally it is not depending upon time, so I am skipping this t or not writing here. And this px square will be pr square upon 2m p theta square upon 2m plus u is a function of r. Now you see that in this expression I am not having theta, so theta is cyclic. Now if theta is cyclic, so what is delta h delta theta? It is 0, and this implies p theta dot is equal to 0 or p theta is equal to constant. Okay. Now delta h, what is the equation of motion? Delta h delta p theta is equal to q, in terms of q, I'll write it in terms of theta dot. So this is equal to p theta upon 2m, let it be a, is equal to theta dot, or theta dot is equal to a upon 2m. In this way you can find your theta and system is described. So you see that if number of cyclic coordinate is increased, the solution of the system becomes more comfortable. So our aim is to find a way so that we can describe a system in terms of we can describe our system in such a way that all the coordinates are cyclic. Now the question is that if we transform our coordinate, one system of coordinate to the another system of coordinate, then how can we get all the coordinates as cyclic coordinates? So for that, first of all, we'll go back to our Lagrangian mechanics and explain that when we transform from one coordinate system to another coordinate system, then what happens in the Lagrangian mechanics and what happens in the Hamiltonian mechanics, right? So suppose I am having a coordinate system in Lagrangian, and that coordinate system is suppose in terms of x and y, and L is Lagrangian for that coordinate system. Now I transform this xy to some another coordinate, say r theta, or you can say rather q1 q2. Then naturally you will get another Lagrangian corresponding to q1 q2. Suppose this is L1 and this is L2, q1 q2. Or I'll explain it in another way. I will stick in the configuration space. In configuration space, suppose your dynamical system is described by a dynamical system is described by a set of coordinate like q1 and q2. Okay, and then or you take it up to n coordinates also. So you take described by qi and qi dot, because now you are in the configuration space. So I am taking all the coordinates which are taken in configuration space. So there is a dynamical system which is described by qi dot and t, and function in the space is Lagrangian L depending upon qi dot and time, right? Now suppose you have transformed these qi to some new coordinates. Now qi are transformed to qi dot under certain rule. Then naturally your si, your q transformed to si, not qi dot. This is transformed to si. Then naturally qi dot will be transformed to si dot, but this transformation is not free. That means the si dot is restricted to certain rule. First of all, when you transform qi to si, you will get some new Lagrangian. So you will get a Lagrangian. Then Lagrangian in terms of new coordinates will be Lagrangian. Suppose it is L tilde, q in place of qi you will have si, in place of qi dot you will have si dot and time. Now how you get this si dot? Naturally your si is a function of qi and time, because there is a transformation between the two and transformation is invertible. So what is dsi dt? That means what is si dot? It is delta si delta qi dot plus delta si delta t. So this is the rule. This is the rule which will provide you s dot. S dot is not free. It is restricted under certain rule. And in this way, our L tilde si dot in time may be written as si is a function of qi and time, or I may write it in reverse way, that I obtain L is equivalent to L if its qi is a function of si and t, and qi dot is a function of si SI dot in time. It simply means that if in your old Hamiltonian you replace your Qi with SI with the help of transformation equations, you replace your Qi dots with the help of SI dot under this rule, and time is already there, then that will be equivalent to the new Lagrangian. It simply means that if a system is described in Lagrangian mechanics and you are having a transformation of coordinates, then the Lagrangian defined by the two will be same. There will be no difference in the Lagrangian, and therefore the Lagrangian equations of motion will also be conserved. What are Lagrangian equation of motion? Lagrange equation of motion for Qi, derivative of delta L delta Qi dot minus delta L delta Qi is 0. And what is the Lagrange equation of motion in SI? d dt of delta L tilt delta SI dot minus delta L tilt delta SI is equal to 0. These will be conserved. Both will be same. This type of transformation is called the transformation in configuration space, and it is known as the point transformation, right? So the transformation is called in configuration space is called point transformation. Now what happens if we transform the coordinates in phase space? Okay, now if I talk about the transformation in phase space, this is the transformation in configuration space, where your S dot is bound to change with the help of a rule which I described earlier. Transformation in phase space. First of all, as I told you that in Lagrangian mechanics, if we transform one set of coordinate to another set of coordinate, and both are describing your dynamical system, then Lagrangian in the two will be same, and the equations of motion will be conserved. But what happens if we do the same in the phase space? In phase space, let your system of coordinate describing the system is Qi, naturally Pi, and time. This is the old system, old coordinates. And you want to transform these to capital Qi, capital Pi, and time. These are the new coordinates. Now what will happen? Transformation is like Qi is a function of small qi, pi in time, and capital Pi is a function of qi, pi in time. So, because your Hamiltonian is obtained with the help of Lagrangian, and it is obtained with the help of Legendre transformation. Therefore, your Hamiltonian in the old and in the new may not be same. It is not derived directly from L. It is derived from L Lagrangian, with the help of Legendre transformation. So if this is your old system, and in this old system, suppose your Hamiltonian is H, and in this new system, suppose your Hamiltonian is defined as K. So these are the two Hamiltonians. But these two Hamiltonians will not be same, and if these are same in any condition, if these are same, then Hamilton's equations of motion will not be preserved. You can very well see with the help of an example. Suppose I am having a system in which the Lagrangian is described as half mx dot square. This is a particle moving along a line, and px is equal to mass into velocity, right? Then I define h. H is equal to, you see here x is absent, so x is a cyclic coordinate. Naturally, h will be defined with the help of Legendre transformation, which provides x dot px minus L. And because x is cyclic from 1, x is cyclic. So this implies delta L delta x is equal to 0, or ddt of delta L delta x dot is equal to 0. And what is this? This is px. Px is constant. This is px. Yes, px is constant. Further, your equation 2 implies mx dot is equal to px. So x dot is px upon m. Why have I tried to find x dot? Because when I am going to define my h, in that h there should not be any term containing velocity component. H will contain only generalized coordinate and generalized momentum. So I have to eliminate x dot whenever it is present in H. Now what is H? H is x dot. What is Px? Px is mx dot minus, or rather I should do in the reverse way. What is x dot? X dot is Px upon m, and Px is already here. What is L? L is half m x dot square, but there may not be any x dot in H, so I'll eliminate this x dot, half m, and x dot is px square upon m square, and solving the two I get upon m. So this is my H. This is H in the old coordinate system, right? Now what is equation of motion for this system? Equations of motion. By definition, x dot is delta H delta Px, and Px dot is minus delta H delta x. So this implies x dot is equal to Px over m, which I have already derived from the Lagrangian, and this implies that Px dot is equal to delta H delta x. H has no x, so it is 0, or Px is constant. So you are getting the same results which you got from the Lagrangian, but these are the equations of motion. These are the equations of motion in Hamiltonian mechanics for the old coordinate system. Now I shift to a new coordinate system. That means there is a transformation between transformation so that I get a new coordinate system. Let x is transformed to y such that now I define my y is equal to x plus v naught t. Suppose this is the transformation equation transforming x to y where v dot is constant, and py in the new system is equal to px. Right? Now define h tilt. H tilt, if I define just by substitution, then my h will be, if I replace px by py here, I get half py square upon m. Okay. And what are the equations of motion? Equations of motion. This is one way of finding these equations of motion. Equations of motion will be y dot x dot plus v naught. This is from 5. What is your x dot? X dot is px upon m plus v dot. So this is your y dot. This is one way of finding the equations of motion. One way. These are equations of motion with the help of these transformation equations. Now I am trying to find the equations of motion from our h, which I have defined here, because both should be same. You see that h and h bar are defined like this. Now with the help of h bar, I get equations of motion as delta h bar delta y is equal to py dot with minus symbol, and delta h bar delta py is equal to y dot. So if I use this one from 6, I get py upon m is equal to y dot. What is py? Py is equal to px, or what is px here? This is py upon m plus v dot, and this is y dot is equal to py upon m. Now you look at these two equations, 8 and 9. This is showing that both the equations are not same. So there is some error. It simply means that if you are having a coordinate system, your dynamical system is described with the help of a coordinate system, and you want to transform that coordinate system, then your new coordinate momentum in new coordinate system is not restricted. It is not depending upon the old coordinate or the new coordinate. And since it is free, you are not getting the same equations of motion. Your equations of motion are not preserved. So therefore, the new Hamiltonian cannot be obtained just like substituting the old variables in terms of new variables. Are you getting my point? In Lagrangian, it was possible that if you have one coordinate system, you are transforming it to the another coordinate system, you are getting the two Lagrangian. The two Lagrangian will be same because there was a restriction. There was a restriction on velocity component to change. It was depending upon the previous coordinate. But in Hamiltonian mechanics, if you are describing your dynamical system in terms of one set of coordinate, you are transforming the set of coordinate to another set of coordinate, then whatever Hamiltonian you will get may not be the same. This will be different. Or what is the another way to get the proper Hamiltonian? The another way is, first you create your Lagrangian in the new coordinate system, you apply the Legendre transformation, and then you get your new Hamiltonian. So now it is clear that if you are getting the two transformation, if you are transforming your coordinate system, then your Hamiltonian or the Hamilton's equations of motions are not preserved. So you cannot obtain your new Hamiltonian just by substitution. So now question is that how the new Hamiltonian is constructed, right? Now the question is that how should we define a transformation which is canonical, and the advantage of that canonical transformation. In phase space, suppose you are having an old coordinate system qi pi, and you want to transform it into new coordinate system capital Qi and pi. You may also take it depending on time. Time may also be a variable there. If corresponding to old coordinates there is existing an Hamiltonian, there exists Hamiltonian H, right? And if corresponding to new coordinates there exists some new Hamiltonian, say K, such that delta K delta Pi is Qi dot and delta K delta Qi is minus Pi dot. If this is true, then you say that your transformation is canonical. This is not the condition because we do not know what is our K. That is, if the structure of Hamiltonian is preserved. I'll talk about the condition of canonicality later. If the structure of Hamiltonian is preserved, then it is preserved, then transformation is called canonical. Now the question is that how we find this transformation. If I talk about the Newtonian mechanics, what happens in Newtonian mechanics? Suppose you have a system, suppose you have a dynamical system described in one set of coordinate and you want to transform it in another coordinate, then there are some specific types of sets of coordinate which will provide you or which will preserve the Newton's equations of motion. For example, suppose your system is described in a coordinate system xy, right? And then in this coordinate system your equations of motion are mx double dot is equal to fx and my double dot is equal to fy. Suppose you rotate this system. You rotate this system and get a new coordinate system by rotating it by 90 degree. So you get a new coordinate system x dash y dash by rotating xy through 90 degree. So you get new equations of motion, and those will be mx dot dash fx dash and my double dot dash is fy dot, and these will preserve the structure of Newton's mechanics, Newton's equations. So this is a specific type of transformation, that if under the orthogonal transformation your Newton equations of motion are preserved and the same result will be obtained. Whatever result is obtained with the help of new coordinate system will be applicable to the old coordinate system. It is all about the Newton mechanics. Suppose I talk about the Hamiltonian Lagrange mechanics. Then in Lagrangian mechanics, agar you are having one coordinate system, you are defining your L there, your equations of motion there, you have new coordinate system which is a transformation which is obtained under such some transformation, then its velocity is restricted. It is true, its velocity is restricted, but just by substituting your old coordinates in terms of new coordinates, old velocity in terms of new velocity, under that restriction you will get a new Lagrangian, and both the Lagrangian will be same and equations of motions will be preserved. But this is not the case in phase space. As I told you earlier, that in phase space, if you are working in one coordinate system, you are having a Hamiltonian there and you are transforming your equations in another coordinate system, then you will get a new Hamiltonian, but it is not necessary that your Hamiltonian is preserved. Your Hamilton's equations of motions are preserved. So what is the condition? That the both should be preserved, or the equations should be preserved. Whatever you obtain from the new coordinate system should be the result if your dynamical system is described in old coordinate system. The way is only to find the canonical transformed equations. That means your transformation from one coordinate system to another coordinate system should be canonical. Now we look at what are the conditions for a transformation to be canonical, right? And how your K will be, or your Hamiltonian will be same in the two coordinate system. You know that we talked about the Hamilton's principle in Hamiltonian mechanics, and yes, we have derived Lagrangian equations of motion with the help of that Hamilton's principle. So what is the Hamilton's principle? Should I change the sheet? Hamilton's principle says that if your system point is moving from one point to another point in the configuration space, then the action integral should be stationary. There are certain conditions naturally for that principle, that your system should be monogenic and all. So it says that delta of f dt from initial time to last time to the final time, this should be 0. This f is some integrand belonging to the action integral. So if this f is L, then L is depending upon qi dot in time, then this principle provides you equations which are Lagrange equations of motion, like derivative of delta L delta qi dot minus delta L delta qi is equal to 0. Now if my L is transformed to H, or I define H with the help of L, then this will be sigma pi qi dot minus H. So you replace this L here, you will get, and replace this F by L here. One implies that delta of sigma pi qi dot minus h is equal to 0, which is known as modified Hamilton's principle. And naturally, now this principle is defined in phase space, because now you are working in h and your h is depending on generalized coordinate and generalized momentum. Modified Hamilton's principle. Right? Now, what are the equations of motion which we derive from this principle? 2 will imply that delta h, delta pi is qi dot, and delta h, delta qi is minus pi dot. These are equations of motion. Right? Now, I have to introduce new coordinate system and naturally a new Hamiltonian. So, before that, I am defining a function. Define a function f. This is capital F in such a way df dt, and it is defined for t0 to t1. Then naturally it will be f for the limits t0 to t1. And if I take the variation delta of df dt dt, then it will be variation of f, and this variation is delta f delta q. This f is a function of qi, pi and t, because you are working in the phase space. Now you are working in phase space. F is defined in the phase space, so f is a function of qi, pi and t. So what will be delta f? This with delta f delta qi, delta f delta pi, delta pi. This is the virtual variation, so we will not write delta t. There is no variation in time. And what about delta qi and delta pi at t0 and t1? At the end time points, there are no variation in the end coordinates. So these are 0. So now I am with delta f, delta qi, delta f, delta pi, and this is equal to delta t लिखने की जरूरत नहीं है, synthesis is equal to 0. So I have defined a function f depending on qi, pi and t, that is defined in the phase space, such that this delta variation of this integral is equal to 0. It simply means that if I add this integrand, if I add this integrand into 2, what will happen? Or if I add this integrand into this integral, this implies delta of t0 to t1 sigma pi qi dot minus h plus df dt is also 0, because it is 0, and I have incorporated this with 2. So 2 implies. Okay. Now what the Hamilton's principle says? Hamilton's principle says that this is 0. If I have added this, this is also 0. But this does not mean that both the integrands in the two expressions are 0. What I want to say that if integrand sigma pi qi dot minus h dt is 0 and delta sigma pi qi dot minus h plus df dt is 0. This does not mean that the two integrands are same. So rather there will be some function which should be present there. So if it simply means that if in old coordinate system delta of sigma pi qi dot minus h dt is 0 and in new coordinate system delta of sigma pi qi dot minus k dt is 0, it does not mean that the two integrands are same. But I may write pi qi dot minus h equal to they may differ by some quantity and let that quantity be df dt. The reason being that integral of this df dt and delta variation of integral of this integrand is 0. So the two will differ by some quantity and I have written this as df dt. So this is an expression which says that f in actual, this f is a function of, this is a function of, h is a function of small p and q. So it is a function of q, pi, these are capital P, capital Qi dot, and k. K is a function of capital Q and capital P and maybe of time. So this is a function of 4n variables and time, right? Secondly, 5 shows that if this left hand side is a perfect differential, then it is an exact differential, or if there exists some f such that this condition is satisfied, then our transformation is canonical because our equations of motion in Hamilton's will be preserved. If left hand side of 5 is an exact differential equation, then the transformation is canonical. So this is the condition for a transformation to be canonical. right? So it is the condition. 5 is the condition for a transformation to be canonical. Now you see this f is a function of 4n plus 1 variables. 4n are the variables in which there are old generalized coordinate, old momentum, new generalized coordinate, new momentum, and then time. But you know that these old and new coordinates are related to each other. You know that your q is a function of qi, pi, and time. Your pi is a function of qi, pi, and time. And these are 2n equations. So practically, your f is a function of 2n variables and one time. So 2n plus 1 variables. And if you rather you can say that this f is a function of 2n variables, and in those 2n variables there may be some new variables, some old variables, and you see you may make the combination of new momenta, old coordinate, generalized coordinate, old generalized coordinate, new momenta, old generalized coordinate, old momenta, new generalized coordinate, new momenta. So there may be 4 type of combinations in which the f may be defined. And secondly, this f is generating your canonical transformation equations. So this f is called the generating function. So hence f is a function of 2n coordinates. You write it here 2n plus 1 coordinate. 2n plus 1 coordinates. And finally, you may define f as a function of n old, n new, and time. You may define f as n old, n new momenta, and time. You may define f as new and then old momenta and time. You may define f as p यानी कि new momenta, old momenta, and time. So there are 4 ways to define this f, and this f is called the generating function. F is called, there is a particular way to write these 4, and those are designated as f1, f2, f3, f4. So there is a specific way to write these 4. F is called generating function. It simply means that if you are having canonical transformation, you have some transformation equations and you have to find whether the transformation is canonical, then if you can find such f, if you can prove that this type of condition is true, then it simply means that your transformation is canonical, and you may also find your f with the help of those equations. And how we do that? Now we will look at an example that how can we prove that a transformation is canonical. You know that this fifth is the condition, which is saying that if your left hand side is an exact differential, then that function, that differential function, that function f is called its generating function. Now how we find the conditions for a transformation to be canonical, or how with the help of f we can find the transformation equations, canonical transformation equations. So first of all, you look at fifth equation. In this fifth equation, if I write sigma pi in place of qi dot, I am writing dqi. Sigma, because it will be dqi dt, so I am ignoring this dt from the whole equation. Sigma pi dqi, and then plus k minus h is df, right? This is our fifth equation. So I have written this k and h together. Okay. And define f as a function of qi, then capital Qi and time. This is called f1, right? Standard name, its standard name is f1. Now I define df. Df will be delta f delta q1 dqi, delta f delta capital Qi dqi plus delta f delta t. So use it in 6 or compare 6 with 7. This is dqi. Naturally, there will be the summation symbols. This is true for all I. The both will be same. So I get delta f delta qi is equal to pi, delta f delta capital Qi is equal to minus pi, and delta f delta t is equal to k minus h. So you got such type of relation, and then you have found your f. K is delta f delta t plus h. So you get a relation between k and h. If you know the h in the old coordinate system, you can define your k with the help of generating function. Now we look at one example that how without finding f you can prove that your equations are canonical. First of all, you look at these equations. 8. If I differentiate this equation with respect to q, then I get delta pi delta qi. And if I differentiate this equation with respect to small qi, then I get capital Pi delta qi, and these two are same. So I get delta Pi delta capital Qi is delta capital Pi delta Qi. Similarly, if I find this equation, this one. If I take this equation and I differentiate it with respect to small qi, delta t, then this is equal to delta k, delta qi, delta h, delta qi, and this implies this delta f delta qi is p. So delta pi delta t from 8a, this is 8a, is delta qi k minus h. You may write like this. Similarly, if I take again, if I consider its differentiation with respect to small q, actually this f is a function of small q and capital Q. So I may differentiate f with small q with respect to small q and capital Q. So now I will differentiate it with respect to capital Q dt. Then this will be delta qi k minus h, or minus delta pi delta t is equal to delta qi k minus h. So finally I get these equations. This one 9, then 10, and then 11. Right? This equation is known as Maxwell relation. And you may get this type of relation for all 4 generating functions. So I'll show with the help of this equation that my transformation equations are canonical because f is indirectly hidden here, right? So I'll not derive any generating function. Rather, I'll have some transformation equations indirectly put here, here, and here. I'll show that my transformation equations are canonical. For that, look at one example. Suppose your q is given as q sin alpha minus p sin alpha, and capital P is q sin alpha plus p cos alpha. Then show that the transformation is canonical. Okay. So one way is to show that transformation is canonical is that sigma pi dqi sigma pi dqi plus k minus h should be exact, right? Or with the help of this relation, I have found that this one delta pi delta qi should be equal to delta capital Pi delta qi. It simply means that you need p, small p and capital P in terms of small q and capital Q, so that I may put this relation over here. And secondly, what was the condition? This was the condition. Delta pi delta t should be equal to this much. Now, look at the question. From equation 1 and 2, from 1 and 2, I'll solve this for small p, and I'll get small p is equal to minus q plus q cos alpha upon sin alpha, and capital P will be 1 upon sin alpha q minus capital Q cos alpha. If you solve these two equations, you will get this type of relation. Now you see that your P, capital P, small p, or capital Q, capital P are not depending upon time. So if these are independent of time, naturally this side will be 0, this side will be 0. And then you are left with K minus H is equal to constant with respect to Qi, and K minus H is equal to constant with respect to Qi. Or now look at this part. From 4 you get delta H delta Pi. First delta Pi, you are just having P, delta P delta Q. Then this will be minus 1 upon sin alpha, 4. And what is delta capital P delta small q? Derivative of P with respect to Q, it is 1 upon sin alpha. So 3 is satisfied. This implies that transformation is canonical. Secondly, you take either this one or this one, and this is showing that since delta Pi delta P delta T is 0, this implies delta Qi K minus H is also 0, or K minus H is a constant, and this constant is not depending upon this Qi. I assume this to be 0. I may assume this to be 0, and so K is equal to H. So in this way, whatever is your old Hamiltonian will be your new Hamiltonian, and these equations, because this condition is satisfied, therefore I may say that transformation is canonical. So this is one way to show that your transformation is canonical, in which you have shown that this is exact. And if you are saying K is equal to H, so if you are saying K is equal to H, what is finally your condition of exactness or transformation equations to be canonical? Pi dqi minus capital Pi dqi is exact. So either you show this, it simply means this is exact, or you show this to be exact, one and the same thing. This is one way to show that your transformation equations are canonical and your Hamiltonian or new Hamiltonian is preserved. Right? Thank you so much.